Okay, everybody, so where we left off, we were talking about the nature of the leaving group, specifically that good leaving groups are able to help an SN1E1 reaction dramatically, while an SN2E2 reaction is less affected by leaving group strength because it has the assist in the nucleophile coming in and giving the leaving group a little bit of a kick in the pants, so to speak. So what I'd like to talk about now is the nature of the electrophilic carbon. So what kind of alkyl X group we're using is going to have a dramatic impact upon whether a reaction is going to proceed through an E2, SN2, SN1, or E1 reaction. Okay, so where we're going to start is we'll start with the SN1E1 manifold here because each of these proceed through a rate-determining heterolysis, or in the slow step of our reaction, we are making a carbocation. And so it turns out this kind of makes sense. Carbocations are extremely high energy species and making them is challenging. And so if we think about producing this intermediate here, what we can see is that the more stable the carbocation that we produce, the lower in energy our transition state is. And so basically this is reflected in the statement up here in that SN1 or E1 reactions form a carbocation in the rate determining step. The more unstable, the more unhappy a carbocation is, the slower the reaction is going to be. In other words, the stability of the carbocation formed is going to map directly upon the ability to do an SN1 or E1 reaction. So let's dig into this just a bit. So I've drawn a reaction coordinate diagram here showing two different alkyl bromides that are going to undergo an SN1 or an E1 reaction. Here we're really just concerning ourselves with the first rate determining step. And so we can see down here we have terbutyl bromide, heterolysis of terbutyl bromide or leaving group loss. We go up and over the hill and we produce a carbocation here, specifically a tertiary carbocation. This is a relatively stable carbocation because of the phenomena of hyperconjugation. So we're able to donate electrons into that positively charged carbon, making it less unhappy than it would previously be. And so because we know our transition state here, is going to resemble in structure the species that it's closest to in energy. So essentially it's closer to this intermediate than to the starting material. This means that our transition state is essentially intermediate-like. It's got a partially formed carbocation. Things that stabilize regular carbocations, like hyperconjugation, will also stabilize a transition state, or a partial carbocation. And what this means then is that a transition state to form a more stable carbocation is actually lower in energy than it would be to form a less stable carbocation. So for example, if we take ethyl bromide here, and you wind up with heterolysis, so we're simply losing our leaving group, what we're going to do is we're going to go up and over a hill here and form a primary carbocation, a high energy intermediate. Again, because our transition state here is going to be intermediate-like in nature, things that destabilize the intermediate, specifically the fact that you can't hyperconjugate a whole lot here, are also going to destabilize the transition state, making it high in energy. So if you have an unstabilized or a destabilized transition state, the hill that you have to climb to get over in your rate determining step is going to be bigger. The higher the hill you have to climb in your rate determining step, the slower the reaction. So in other words, walking up the hill from res rec takes a lot more energy to get to class than, let's say, if you're in the School of Business and Entrepreneurship and you can basically walk downhill slightly. So it requires less effort, so less activation energy to make sure you're on class on time. And so because of this, the more stable the carbocation you form, or can form with your substrate, the faster you're able to undergo an SN1 or an E1 reaction. So let's think about what this means in sort of the different types of substrates we can have. If you need to pause the video to make sure you have everything written down, please feel free to do so. And when you're ready, hit play again and we'll start talking about carbocations. Welcome back. So now I'd like to talk about the different types of carbocations that we can form in an SN1 or an E1 reaction. So what I've drawn up here is the relative carbocation stability scale. So we talked a little bit about this 2 chapters ago, but this is worth just a little bit of a review. Remember, carbocations that can be stabilized by resonance, such as this benzylic carbocation here, or this allylic carbocation here, are the most stable carbocations you can make, because we're spreading that positive charge out over multiple carbons. Following this, tertiary carbocations are more stable than secondary, which are more stable than primary carbocations because of differing amounts of hyperconjugation. The better you're able to hyperconjugate with that positive center, the better able you are to distribute that positive charge, making the carbocation easier to form and happier, so to speak. Going down here, we have a methyl carbocation where there's no hyperconjugation possible. And this is much more stable than what we consider our vinyl carbocation or our alkynyl carbocation here. And the reason that these are stable is because we're placing that positive charge in an orbital that has a higher amount of s character. Remember, s orbitals hold things closer to the nucleus. So if we have a greater amount of s character, we're taking that positive charge and putting it smack dab up against the positively charged nucleus. And let's be honest, it's just not happy. So what you can think about is in terms of carbocations, these guys here are in a category that I like to refer to as nope, in that you simply can't make them. They're too high in energy to make them outside of a specialized reaction where, like a pea chemist, you're going to heat some things up to a bajillion degrees and say, haha, I made it. In a standard reaction flask, you can't have this. And so the cool thing about this is because you understand the stability of carbocations, you now, by extension, understand the ability of species to undergo an SN1 or E1 reaction. So for example, benzylic or allylic halides, I've just added bromine here because I like bromine, are going to be the most reactive in an SN1-E1 reaction because they form the most stable carbocations. This is followed by tertiary, secondary, and primary alkyl halides respectively in that order because of the differing stability of carbocations that were offered. And then finally down here, you've got primary and methyl carbocations, or excuse me, alkyl halides, followed by vinyl, or in this case, alkynyl alkyl or alkynyl halides. And so it turns out that in an SN1-E1 reactivity scale, once you get lower on this scale than a secondary alkyl halide, this is simply too difficult to do. The reaction is slow enough to the point where you're not going to make any appreciable product. So in summary, when dealing with E1 and SN1 reactions, the ability to undergo these reactions is directly dependent upon the stability of the carbocation formed. And so because of this, things like benzylic bromides, or halides more generally, allylic halides, and tertiary alkyl halides are very good at undergoing SN1 or E1 reactions. Secondary alkyl halides are acceptable. They're slow, but it can happen. Anything where you form a carbocation less stable than that is simply too slow to actually work. Okay. So the nifty thing about substitution is that the selectivity for an SN1 or an E1 reaction is actually opposite that of an SN2 or E2 reaction. So if we look at a reactivity scale, so a similar type of reactivity scale for the bimolecular reactions, so SN2 or E2, we'll start with SN2 here. We can see that for SN2 reactions, we are extremely sensitive to the size of the electrophile. And what we mean here is essentially the number of carbons attached to the carbon, so our alpha carbon here, that is making that carbon-leaving group bond. And so in an SN2 reaction, methyl X groups react extremely quickly, followed in reactivity by primary alkyl X groups, and then secondary alkyl X groups. So like SN1 or E1, secondary alkyl X groups are acceptable in terms of using this as a substrate, meaning it's slow, but it can indeed happen. Once you get bulkier than the secondary alkyl X, such as a tertiary alkyl X, this is simply too sterically bulky to go ahead and have this form product at any appreciable rate. It's simply not going to happen. And so let's think about the reasons for this. And the reasons for this are actually directly related to steric encumbrance. And so I've drawn an example reaction here of terbutyl bromide reacting with a generalized nucleophile. So this is just a nucleophile like hydroxide or hydrosulfide, something with a nice lone pair of electrons that's able to act as its nucleophilic source. And so in order for this reaction to happen, remember an SN2 reaction requires that you go ahead and overlap the lone pair of electrons or the pair of electrons in your nucleophile with the lowest unoccupied molecular orbital of your electrophile. And in this case, our LUMO, or lowest unoccupied molecular orbital, is going to be the sigma star of this carbon-bromine bond. In other words, the anti-bonding orbital of the bond we are trying to break. So the problem with this is we need to directly have physical and spatial overlap of two orbitals. Okay? If you have a bunch of junk in the way of the ability to go ahead and overlap those highest occupied molecular orbitals with the lowest unoccupied molecular orbitals, you're not able to have effective bond overlap. Without effective bond overlap, you can't form a bond, and more importantly, you can't cause this carbon-bromine bond to break. And so at a certain point, the steric encumbrance becomes too much for the reaction, and it simply will not work. And that line of where it's slow versus just too much really falls at this secondary alkyl X, and between that secondary alkyl X and the tertiary alkyl X. And so generally speaking, we've got a pretty good idea for substitution of what something is going to undergo in terms of its reaction mechanism. So SN1 and E1 work really well with very stabilized, or quite honestly, bulky electrophiles. On the other hand, SN2 reactions work well with non-bulky electrophiles. And so depending upon the steric bulk of the electrophile, you can make a pretty good prediction of whether something is going to undergo a stepwise substitution, or SN1, or a concerted substitution, or SN2. So this is the end of this video. What we're going to do next is I'm going to fill you in on how the sterics of the electrophile, so specifically the steric bulk of the alkyl X group, how this affects E2 eliminations. And then after that, we're going to put this all together to decide, okay, I've got an alkyl X and an attacking species, what happens? Stay tuned.